Uh, there is one example in this slide. So in this example, we want to consider a realistic situation that often occurs in operational solar farms. Let me add a new student. Okay. Imagine that utility scale solar farm suddenly experiences a drop in its power output. So this is a first assumption. Um At the first glance, this may appear as a simple generation issue, but in practice, it can be caused by multiple factors, and identifying the root cause is an important energy task. So one of the very important engineering analysis. So there are several possible reasons for this behavior. One common reason is environmental conditions such as sudden cloud coverage or dust accumulation on panels or partial shading. Shading is very important in the solar panels. So, and also dust, humidity is very important. So all of these factors directly reduce the amount of solar irradiance reaching the photovoltaic modules, and at the end we will have less power output. So another possible reason is a technical fault, such as an inverter malfunction or shutdown, since inverters are responsible for converting DC power to AC power. Any failure at this stage will immediately affect the usable output of the system. So we also need to consider longer term effects such as panel degradation or localized hot spot, which can reduce efficiency over time. So uh, all of the components has a degradation cost. So after a few times, the output will be reduced. In some cases, the issue may not even be physical. It could be related to grid disturbances, communications errors, or or faulty sensors in the monitoring system and so on. So the key questions here is that how do we realize the root cause of the solar farms? To answer this, we need to analyze multiple sources of data. This includes real-time DC and AC power measurements, inverter status logs, weather and irradiance data, module temperature reading, and SCADA system alarms, and so on. So if we have SCADA systems, we need also uh, consider the SCADA systems, SCADA alarms. So by combining those data sources, we can isolate whether the problem is environmental, electrical, or system related, and uh, we can diagnose those faults. This type of analysis is very important in real-world renewable energy systems, where fast and accurate fault detection directly impacts system reliability and also, of course, energy production. All right. In this slide, we want to focus on the main components of wind energy systems and how they work together to convert wind energy into electrical power. The first and most visible component is the rotor blades. These blades are designed using advanced aerodynamic principles to capture kinetic energy from the wind. So when wind follows over the blades, it creates more forces that cause the um, rotor to move on, And the efficiency of this process depends strongly on blade design, wind speed, and air density. Next, we have the gearbox, which is used in many conventional wind turbines. The role of gearbox is to increase the relatively low rotational speed of the rotor to a higher speed suitable for electricity generation. However, in some modern turbines, direct drive systems can be used instead, and eliminating the gearbox and improving reliability by reducing mechanical complexity will be applied in such a system. So, in third, the third key component is the generator. This is where mechanical energy is converted into electrical energy, and most wind turbines use either induction or synchronous generators, depending on the design and application. And the generator is a critical component because it directly determine it directly determine um, the quality and efficiency of the electrical outputs. And finally, we have the control system, which plays a very important role in both performance optimization and system protection. The control system adjusts the pitch angle of the blades and the yaw direction of the turbine to ensure maximum energy capture. It allows protects the turbine from extreme wind conditions by reducing load or shut down the system when needed. So in summary, the rotor captures energy, the derivation transfers it, and the generator converts it, and the control system ensure optimal and safe operation. Together, these components form the foundation of the wind energy system. So uh, we need to uh, take care of take care of each these components in order to make sure that the reliability of the system is in allowable range. Okay, in this slide, I want to discuss two of the most critical failure mechanisms in wind energy systems: blade failure and gearbox failures. Let me start with the blade failure. Wind turbines blades are constantly exposed to changing and cycle wind loads. These loads vary in intensity, direction, and frequency, which means the blades undergo continuous mechanical stress during the operation. Over time, this repeated loading leads to failure in the composite materials used in blade construction. So failure does not usually cause immediate failure. Instead, it develops gradually in the form of macro cracks and structural weakening. So the structure can be weak. So these small defects can grow over time and eventually lead to significant damage if not detected early. That's why reliability here is very important. This can reduce aerodynamic efficiency, increase vibration, and it severe cases results in partial or complete blade failure. So therefore, regular inspection and condition monitoring are very essential for early detection. So now let's move to gearbox failure. The gearbox is one of the most mechanically stress components in a wind turbine. It is responsible for increasing the low speed rotation of the rotor to a higher speed suitable for electricity generation. Because of high torque loads and variable operating conditions, the gearbox is subject to significant mechanical stress. So common failure mechanisms include bearing wear, lubrication, degradation, gearbox cracking, and misalignment are the main common failures in the system. So these issues can develop over time and often lead to sudden and costly failures. Gearbox replacement or repair is one of the most expensive maintenance operations in wind turbines and can cause long downtime for the entire system. In summary, both blade fatigue and gearbox failure significantly affect wind turbine reliability, and they not only increase maintenance costs but also reduce system availability and energy production. This is why condition monitoring, predictive maintenance, and improved design are most important and very essential for improving the reliability of the wind energy systems. So in this slide, I want to focus on the key types of data used for monitoring and analyzing wind turbine reliability. Modern wind energy systems rely heavily on data-driven approaches to ensure safe and efficient operation. The first important variable is wind speed. So wind speed, the primary input that determines how much energy can be extracted from the wind. And since power generation is strongly dependent on wind speed, accurate measurement and forecasting are very essential. And wind speed data is also used to identify abnormal operating conditions such as sudden drops or extreme gusts, or which may indicate systems or environmental issues. The second important parameter is temperature. The temperature plays a critical role in the performance and reliability of the key components such as the generator, gearbox, and power electronics. Excessive temperature can indicate overheating, poor cooling performance, or mechanical stress. Additionally, temperature variations affect lubrication properties and accelerate material aging. Therefore, continuous temperature monitoring helps in early fault detection and preventive maintenance. So the third key data source is vibration. So what is a vibration? Vibration analysis is one of the most powerful tools for condition monitoring in wind turbines. Mechanical components such as gearboxes and bearings generate characteristic vibration pattern during the operation. Any deviation from normal vibration behavior can indicate developing faults such as misalignment, imbalance, or bearing wear. By analyzing vibration signals, you can detect faults at any early stage and prevent actually any future failures. In summary, all of wind speed, temperature, and vibration together provide a comprehensive view of both operational performance and mechanical health. When they can be combined, these data sources enable predictive maintenance strategies, improve reliability, and reduce unexpected downtime in wind energy systems. On the other hand, what I want to say here is that first you have to realize what is your input data. Then you can make a plan to how you can increase the reliability of your system. In this slide, I want to introduce an important concept in wind energy reliability modeling, which is the Weibull distribution. The Weibull distribution, I already talked about Weibull distribution. I wanna because Weibull distribution is mostly using in wind speed variability, so that's why I put here again. So the Weibull distribution is widely used in wind energy power to model wind speed behavior over time, and um, unlike normal distribution, wind speed is not symmetric and uh, does not follow a simple Gaussian pattern. Instead, it is typically skewed and with many moderate wind speeds and fewer extreme values. So the Weibull distribution is able to accurately represent this real world behavior, which makes it extremely useful in energy system analysis. Mathematically, the Weibull probability density function is defined using two key parameters: the shape parameter denoted by K and the scale parameter denoted by C. The shape parameter controls how variable the wind is, and a lower value of K indicates more variability, while a higher value indicates more stable wind conditions. And the scale parameter C is related to the average wind speed, and therefore reflects the overall energy potential of a site. So from an engineering perspective, these two parameters allow us to characterize wind resources in a very effective way. By fitting wind data to a, Weibull distribution, we can estimate how often different wind speed occur, which is essential for predicting energy production. So this model is widely used in several applications. First, it is used in energy yield estimations, where we calculate how much electricity a wind farm is expected to produce over time. So second, it is used in site assessment, helping engineer determine whether a location is suitable for wind energy deployment or not. Third, it can support reliability analyzing by allowing us to model the variability of the energy sources. Finally, it is used in turbine selection and optimization, ensuring that the chosen turbine design matches the wind characteristics of the site. In summary, if I want to summarize this slide, the Weibull distribution is in regarding the wind turbine modeling is a fundamental tool in wind energy systems, because it can provide a realistic and practical way to model wind speed behavior, which directly impacts both energy production and system reliability. Okay, in this slide, I want to discuss one of the most important modern approaches to maintaining reliability in wind and renewable energy system in total, predictive maintenance. So probably we can apply these methods in other applications as well. So predictive maintenance is a strategy where maintenance activities are scheduled based on the actual condition of the equipment, rather than on a fixed time interval or after a failure occurs. So, in other words, instead of waiting for a component to fail or performing maintenance at regular intervals, regardless of condition. We continuously monitor the system and act only when there are clear signs of degradation. So this approach relies heavily on data. Key inputs include vibration measurements, temperature readings, wind operating condition, SCADA system data, and historical failure records. So these data sources provide comprehensive view of both the operational and mechanical health of the system. The process typically begins with data collection from a sensor installed on the turbine. So this data is then analyzed using signal processing and machine learning techniques to assess the condition of the components. So the machine learning techniques are using widely um, regarding the prediction. Uh, Engineers look for patterns and or trends that indicate early signs of faults. Based on this analysis, it is possible to estimate the remaining useful life of a component. So often referred to a remaining useful life (RUL) estimation. I mentioned here. So and then schedule maintenance before a failure actually occurs. So the main advantage of predictive maintenance is that it significantly improves system reliability while reducing operational cost. It helps avoid unexpected breakdowns, minimize downtime, and extends the lifetime of expensive components such as gearboxes and generators. In addition, it allows maintenance resources to be used more efficiently since interventions are only performed when necessary. In summary, predictive maintenance represent a shift from reactive and scheduled maintenance toward a smarter, data-driven strategy, and it is a key enabler for reliable and efficient operation of modern wind energy systems. In this case study, I want to analyze the real-world issues in wind energy systems, turbine downtime. So wind turbine downtime refers to the period when a turbine is not producing electricity due to failures and maintenance or environmental condition. Even small increases in downtime can significantly affect annual energy production and economic performance, especially in large wind farms. So this key point is very important. In this example, I want to consider a turbine that experiences repeated and unexpected downtime events. The main objective is to identify the dominant causes of this unavailability and propose strategies to improve system reliability. The downtime can generally be categorized into several groups. First, we have weather related shutdowns, where turbines are stopped due to extreme wind speeds or uh, safety conditions. Second, mechanical failures such as gearbox or bearing issues can lead to significant outages. Third, electrical failures involving the generator or power electronic converters can interrupt the energy conversion. And fourth, control systems or sensors um, may cause incorrect operation or false alarms. Finally, scheduled maintenance activities can also contribute to planned downtime, although these are typically more predictable. So to evaluate performance, we usually use the key reliability indicators such as turbine availability, energy production losses, mean time between failures, and mean time to repair. So we already discussed about all of these key performance indicators we call KPI. These matrices help quantify both the frequency and the severity of downtime events. And the key question here in this case study is which failure uh, which failure mode contributes most to downtime and how can it be reduced, so by analyzing operational data, maintenance records, and fault logs, you can identify the most critical issues and prioritize improvements. For example, if mechanical failures dominate predictive maintenance and improve component design may be required, and if electrical faults are significant, better converter design or protection systems may be needed. In conclusion, downtime analysis is a powerful tool for improving wind turbine reliability, and it always um, engineers to move from reactive maintenance toward data-driven decision making and ultimately improve energy yield from the wind turbine and system, increasing the system performance. Okay, in this final discussion side, I want to focus on a very important engineering question. How can we reduce failures in renewable energy systems? All right. As we have seen throughout this section, both solar and wind energy systems are subject to different types of failures, including mechanical degradation, electrical faults, environmental impacts, and control system issues, and so on. Therefore, improving reliability in this case requires a multi-layer approach rather than a single solution. One of the most fundamental approaches is design improvement. By designing more robust components, improving thermal management, and adding redundancy in critical subsystems, we can significantly reduce the probability of the failure. Another important area is monitoring and diagnostics. Modern renewable energy systems are increasingly um, equipped with sensor and SCADA systems that allow real-time monitoring. So all of these equipments enables us early detection of abnormal behavior before it develops into a serious fault. So a third um, key strategy is maintenance optimization, especially predictive and condition-based maintenance. And instead of reacting to failures, we can anticipate them using data-driven methods and schedule maintenance in advance, reducing downtime and repair costs. In addition, data analytics and artificial intelligence are becoming increasingly significantly important, and machine learning algorithms also can detect patterns, predict failures, and estimate the remaining useful life of components, which significantly improve decision making. Finally, we must also consider system level solutions such as integrating energy storage, hybrid systems, and smart grid support. These solutions not only improve reliability at the component level, but also enhance overall system stability and flexibility. In conclusion, reducing failures requires a combination of engineering design, advanced monitoring, intelligent maintenance strategies, and system level integration. So the most effective approach is usually a combination of all these methods working together and find the best solutions to um, optimally and accurately operational of the system. Here in this slide, I want to introduce the fundamental architecture of an electric vehicle system. Understanding these three main components is essential for analyzing both performance and reliability in electric vehicle. So the first and most critical component in electric vehicle is a battery pack, right? The battery serves as the main energy storage unit in an electric vehicle. It supplies direct current power to the entire system and largely determines the driving range of the vehicle. Most modern EVs use lithium ion batteries due to their high energy density, efficiency, and relatively long cycle life. However, batteries also introduce challenges such as degradation over time, thermal management issues, and also safety concern. So the second key component in electric vehicle is the electrical motor. The motor is responsible for converting electrical energy into mechanical motion, which ultimately drives the wheels of the vehicle. Electric motors are highly efficient, often exceeding 90% efficiency, which is significantly higher than internal combustion engineers. And different types of motors are used in electric vehicle, including the induction motors and permanent magnetic synchronous motors. Depending on the performance requirement and cost consideration, we can use one of these type of motors. The third essential element is a power electronic device. So this includes inverters and DC to DC converters, which manage and control the flow of electrical energy between the battery and the motor. And power electronics here play a crucial role in controlling vehicle speed, torque, and overall efficiency, and they all also enable important functions such as regenerative braking, where kinetic energy during braking is recovered and stored back into the battery. In summary, the battery provides energy, the power electronics control and convert it, and the motor converters convert it into motion. So these three components forms the backbone of any electric vehicle systems and are tightly interconnected in terms of both performance and relatively. Okay, in this slide, I want to discuss why reliability is a critical factor in electric vehicle systems, focusing on two main aspects: safety and cost. First, let's see, consider the safety. Safety is the most important requirement in any electric vehicle system. Electric vehicle operate using high voltage battery systems typically ranging from 400 volt to 800 volt, or even um, higher high voltage battery systems, and any failure in the battery, power electronics, or electrical installations can lead to serious safety risk, including overheating, electrical faults, or in extreme cases, thermal runaway in the battery system. So thermal runaway is particularly critical because it can lead to fire or explosion if not properly controlled. Therefore, a reliable system design, advanced battery management system, and continuous monitoring are essential to ensure the passenger safety. In addition, stable operation of the motor and power electronics is necessary to prevent sudden torque losses or uncontrolled behavior of the vehicle. Now, move to the second aspect, cost. Reliability has a direct impact on the overall cost of electric vehicles. One of the most expensive components in an electrical vehicle is the battery pack. If the battery degrades quickly or fails permanently, it significantly increases maintenance and replacement costs. So similarly, failures in power electronics or motor systems can result in expensive repairs and downtime. From a manufacturer perspective, poor reliability can also lead to increased warranty claims and reduce customer trust. From the user perspective, reliable systems reduce the total cost of ownership, including maintenance, charging efficiency, and long-term operational costs. Therefore, improving reliability not only enhances technical performance but also makes electrical vehicles more economically attractive and sustainable in the long term. In conclusion, reliability in electrical vehicle is directly linked to both safety and cost, and a reliable system ensures passenger protection and also reduces life cycle expenses, making electric vehicles more practical and competitive. So, um, is there any question? All right. In this slide, I want to focus on two major reliability challenges in electrical vehicle batteries. First of all, degradation and thermal runaway. Let's begin with battery degradation. Battery degradation refers to the gradual losses of battery capacity and performance over time. In electrical vehicles, batteries undergo repeated charge and discharge cycles, and each cycle contributes slightly to the aging process. In addition, factors such as high temperature, fast charging, deep discharging, and high current loads can accelerate this degradation. So as the battery degrades, its ability to store energy decreases, which directly reduces the driving range of the vehicle. This is one of the most noticeable effects for users. Over time, degradation also affect charging efficiency and overall system performance. Although degradation is a slow process, it has a significant long-term impact on reliability and life cycle cost. So, and now let's move to the second and more critical issue, thermal runaway. So thermal runaway is a rapid and uncontrolled increase in battery temperature. It is usually triggered by internal faults such as short circuit, physical damage, overcharging, or manufacturing defects. Once thermal runaway begins, the heat generated inside the battery increases exponentially, making it very difficult to control. This uh, two phenomena is extremely diagnosed because it can lead to fire or even explosion in several cases. Unlike degradation, thermal runaway is a sudden um, and very common event, and therefore electrical vehicle battery system must be equipped with strong safety mechanisms, including battery management systems, thermal monitoring or cooling systems, and protective circuits design. If I want to summarize this slide, battery degradation represent a long-term performance decline, while thermal runaway represents a rare but critical safety risk. So both must be carefully managed to ensure reliable and safe operation of electrical vehicles. Okay, I wanna stop my lecture here. So, is there any question?